Well, now on to the last section of Lecture 17, which is the last lecture of the course, the core element of the course. And we're going to look at transmitter-receiver architectures, how all these things can fit together in different architectures. And then we'll summarize the lecture on transmitters and receivers. Okay, we've got transmitters we've shown you that are dish antennas and array antennas. And we've shown you all different kinds of array antennas, active and passive scanning, hybrid antennas, and dish versus antennas. And so what we want to do is address the architectural issues. A number of these architectural issues were addressed in pieces. And what we want to do in the antenna lectures. And what we want to do is to put them all together in context of how they scan a volume and why one would be used versus another, and how we put them together in an overall system. And they would be the dish antennas, array antennas and their different types of scanning, and hybrids. And so here we have a perfect example of a dish antenna and a perfect example of an array antenna, the Patriot's antenna. Okay, here are some perfect examples of a passive array antenna, which would mean there's some big tubes in here and waveguide goes out and is fed to the elements in this phased array. Or you could have an active antenna where you have transmit-receive modules out at each element. Or if it's a thinned array at every nth element or whatever. But you can have active array elements, and we talked about passive array elements, where we have a big tube and you feed high power or low power from a transmitter exciter would go into each of the TR modules. So we've got those. Now let's look over the architecture's big picture. Pros and cons. For a dish radar, we've got the lowest of cost. And we've got frequency diversity as a pro for those. The cons are, you've got its dedicated function. You're really tracking one target or a very close cluster of targets. It's got a very slow mechanical scan rate because of the innate inertia of a mechanical antenna. It requires a custom transmitter, and it's got higher losses. Passive array antennas, we would have a transmitter, high power, and a receiver, and you'd go out to the array where you'd shift the phase at the array face, and they're the pros. So you got beam agility, and you can effectively manage the resources because you can shift the phase shifters around to move the beams back and forth, and you get rid of the problem of the slow motion of the antenna here. But you've still got the transmit and the receive. An active radar, you've got beam agility, effective radar sources, effective radar resource management, low loss, higher costs in both of these, and more complex cooling if we did the transmit both here and here. The thing that I did not mention were the cons in the passive array, which are it is also higher cost, and it requires a custom transmitter and high power phase shifters. These phase shifters got to be able to handle the high power from this big transmitter, and it's got higher losses. We're going to look at that in a moment. In active arrays, there's a low power transmitted pulse goes out to TR modules, and the power can be distributed to through a subarray section where we'll divide the power up, and each phase shifter is different in each transmit-receive module, and it will go out to different subarrays, and we'll transmit out all of our different elements in TR modules. Each phase shifter is in a TR module. So we're doing the phase shifters and the transmit function and the receive function with this kind of an active array here. And the receiving functions go right back the same. And they're going to be low power, obviously, and they're going to go into the A to Ds in processing. Here are two active array antennas which use active phased arrays with transmit-receive modules. The THAAD X-band phased array radar, which is used for missile defense, and the C-based radar. It's an X-band phased array radar that's mounted on this huge oil drilling platform. And it's got 45,000 elements in it and a mere 25,000 transmit-receive modules in it. These are both very, very costly systems. So you can see how cost can come into play. Now let's look at a block diagram of an active radar array using TR modules. Each TR module contains filtering, amplification, and amplifier phase control. And they're all in the TR module. And there's an antenna for that TR module at the output. And so you'll have in an array antenna N by M, if it's rectangular, TR modules. And you'll have timing, and a waveform generator will send signals in. There'll be control connections for timing and sending what the appropriate phase shifters should be to receive at a given angle. And the amplification control, the low noise amplifier, the receiver output will have to be at the correct phase to receive energy from the angle that you're interested in, and then it will go through a beamformer where you'll take these outputs from all the different arrays and you'll combine them to form a beam. And then you'll go through the local oscillator, receiver, A to Ds, IQ, division into your real and imaginary part, and then into the processor. This is the overall block diagram. If you look at it simply, what you have is a phase shifter that's going to shift the phase appropriately, and on transmit it's blue, and on receive it's red. And you send the signal out, you go through a TR switch, amplify the signal, it gets switched here and then out the antenna. When it comes back in, you have a low noise amplifier, and then it's switched to the phase shifter to have the correct phase, and then it goes out to join the myriad of N outputs. Just imagine, in the tens of thousands for those two large antennas I showed you. Okay, for power amplification, the low power would come from a waveform generator, and then when I say in the transmitter, the driver amplifiers, I mean the power amplifier that would come out of the waveform generator may need one stage of power amplification. It may need an intermediate power amplification before it goes on to the really big guy, like those the TWTs or the klystrons, the high power amplifier. So these are called the driver amplifiers, and depending upon how much RF power you want to go out to the antenna, you may or may not need them. If you have tens of thousands of elements that are all sending energy out in a given direction after combining by phase, you don't need a lot of amplification of the transmitted signal from the waveform generator. But the amplification will occur for given usage in multiple stages, usually 2 or 3, with a driver amplifier, it's also called, and then the high power amplifier. And each stage could be a single amplifier or several in series or parallel. And there are requirements for the power amplifier here. We want low noise, minimal distortion, minimal combiner losses if we have multiple amplifiers in the configuration. And here's an example of power amplification in a TR module. And you can see we have the transmit receive elements don't have to be, I want to remind you, the size of an inch by 2 inches. They could be the size at UHF frequencies of what I remember of about 7 inches, 6 inches by 12 to 13 inches. So you've got some size to put componentry in. And here we have each of these triangles is an amplifier. We have the RF in and the transmit receive switch when we're transmitting. These is a pair of driver amplifiers in series, followed by another driver amplifier in the high power amplifier. And you can see we've got here a series of 4 sets of amplification to generate the total power going out and that we need. And then again, we'll have a TR switch or circulator where it will come in, have protection, low noise amplifier. This protection obviously implies that we've got pretty high power here. Something like one of those big early warning radars or ballistic missile early warning defense radars, TR switch, and then phase shifters, and then the RF would go out. And so higher transmitted power can be combined. This is just to show you with multiple stages. It's more complex, and you're going to have combiner losses. The lower the better. Now, what we can have also with an array antenna is we can digitally receive up at the TR module. So what we can do is we can have an analog TR module where we, right at the TR module, we can have an A to D converter built in with every TR module. First you might sum a number of beams and then sum a number of other beams before we go into the that one analog TR module would sum, and then you'd have the phase shifters outside of it. But then we could receive from the A to D converters in multiple channels, and then we could digitally do digital beam forming. So we could, in parallel, do digital beam forming and have multiple receive beams. And so an analog TR module receive signal is immediately digitized by the A to D converter after the phase shifters are done and things are summed. So the digital beamformer generally receives, the digital beamformer digitally will generate multiple receive beams. If you wanted to set up a wide vertical or horizontal set of beams, this would be an ideal array. And to take it to the final extreme, you can have the entire digital section in each TR module, where we digitally go from the waveform generator right into each TR module to the digital section in it, in blue, for each one, and then have the A to D built into the TR module, and we'll have an analog section up front, and we digitize right at the RF, or have an appropriate mixer down so that we can, and so that we digitize and then go to make the digital beam forming here. So digitization of the waveform generator and the receiver data are performed within each module, and this makes our transmit-receive options very, very flexible. So now, in summary, and this in the transmitters and the receivers, we've gone over the transmit function, which usually is divided into 2 parts: the waveform generator, which creates the low power waveform signal, which is up-converted to RF, and then the power amplifiers, which can be a chain of them or a single one, and they'll amplify the RF signal up to the appropriate level, and both tube and solid-state amplifiers can be used. The tubes can be huge power, and the solid-state amplifiers can be very small, built in on a chip with MMIX technology. And the radar receiver portion, filtering, amplification, and down conversion signals functions. We've looked at those in detail, and how the signal is digitized and sent down to the signal processor in a variety of architectures. And there are very many different ways to put these architectures we've looked in the last section. And they'll depend on the antenna type, the function of the system mission you have, the centralized architecture with dishes or passive array radars, and distributed architectures evolving for both active arrays and digital array radars. Continued in the summary, we've shown that the big tubes that can be used, klystrons, TWTs, CFAs, they're usually used to generate high power electromagnetic energy in the microwave region for dish radars. Solid-state microwave transmitters are now available. They're more expensive, more reliable, and the solid-state TR modules are used, and in low-power dish radars. And duplexes are used to isolate TR switches, to isolate the receiver's high-power signals from the very sensitive radar receiver. And for homework problems. Now, since this has been one beefy course with an awful lot in it, if you've had enough patience to go in and go through it, I'm assuming you've had the intellectual growth to do part of what I'm going to assign here. From Skolnick, that's reference 1, I'd like you to do problems 1 through 5, which aren't that bad, in Chapter 10, and problem 8 in Chapter 10, and then problems 11, 9, 10, 12, 10, 15, and 10, 16. And then, although it's not covered in lectures, I want you to read about receiver noise figures and how they're calculated in sections 11.1 through 11.3, and they're about 20 pages in the receiver chapter, and then do these 4 problems. Now going on to the references. These are the references I've used in putting together this last lecture. And I'd like to very much thank Dr. Doug Carlson of MACOM and the colleagues at Carbon Systems for providing those waveguide, and also Dr. Jeff Hurt from MIT Lincoln Laboratory for a lot of the ideas for the view graphs he has used in Lincoln Laboratory. And you'll see a number of the different view graphs I thank Lincoln Laboratory used with their permission. They were from Jeff's idea.